In the last section, we talked about performing calculus with our vector-valued functions, specifically derivatives and antiderivatives. And in this section, we are going to use them for some application problems and see what exactly derivatives and antiderivatives can help us with in real life when we perform them on these vector-valued functions. So in application problems, we typically think of R of t as being a position vector. So these blue arrows that you see are position at different times. And even though they are vectors, we can also consider the components we get back from the position vector as points. So the way that I like to always think of this is this black graph represents the path of a particle moving through space. And as we plug in different times to the position function, it will tell us where the particle is located at that point in time. R prime of t, which you might also see as v of t, is our velocity vector. The velocity vector is always tangent to our path. It's always a tangent vector. And we can get the velocity at any particular point in time by plugging the time into the derivative. The magnitude of our velocity vector, which we just use our normal magnitude formula that we learned all the way back in the first section, represents speed. So that's taking these velocity vectors and just calculating magnitude. Remember, typically, since velocity is a vector, we consider it to have magnitude and direction. If we just want to know the magnitude portion of it, we can do that as well, and it's called speed. And then finally, our second derivative is acceleration. And acceleration at any point in time will tell us both how our position is changing and how our how our speed is changing and how our direction is changing. Because it is the derivative of velocity, it tells us how velocity is changing. And since velocity has speed and direction, acceleration tells us how speed and direction are changing for our particle as it's moving along this path. So we're just going to do a quick example with some calculations. Suppose we have a particle that's moving along a path given by R of t equals 2e to the t minus 3i plus t squared minus 2j plus 5tk. And we want to find each of the following. The position at time 3, the velocity, the speed, the acceleration, all at time 3. So R of t is position. So to find position at time 3, all we have to calculate is R of 3. So we're going to plug 3 in for all of the t's. And when we do that, we get 2e to the 3 minus 3i plus 3 squared minus 2j plus 5 times 3k, which after we simplify, this tells me that my particle, after 3 seconds or 3 minutes or 3 hours, we didn't assign a time unit here, our position is going to be 2i plus 7j plus 15k, or we could also just think of this as the point 2, 7, 15. This locates just a single point in space where our particle is located after a time of 3. For the velocity of our particle, we need to calculate our derivative. V of t is r prime of t. So before we plug our 3 in, we first need to calculate derivative. So the derivative of 2e to the t minus 3 is 2e to the t minus 3. The derivative of the e is always itself, and then times the derivative of the exponent, which in this case is just a 1. The derivative of t squared minus 2 is 2t for our j component, and the derivative of 5t is just 5 for our k component. And now we can plug in 3, and we get 2i plus 6j plus 5k. So this is velocity. it tells us both a magnitude and a direction for how our position is changing. For speed, we just want the magnitude of our velocity. It's just one of the components of our velocity function. And that's just our normal magnitude formula where we square each of our components and add them together under a square root. So this is going to be 4 plus 36 plus 25, which is the square root of 65. Usually with speed, you might think when you're driving, like in miles per hour or meters per second. So radical 65 might not tell us a whole lot of information. You can change this to a decimal as well. And we have a speed of 8.06 units per time. And then lastly, our acceleration. That's going to be our second derivative to get acceleration. And to get the second derivative, you just take the derivative of your first derivative, which is right here. So we're going to take the derivative for each of those components one more time, and we get 2e to the t minus 3i plus 2j. And then in our velocity function, our k component is a constant, so its derivative is 0, which means our acceleration at time 3 is going to be 2i plus 2j plus 0k. So the 0k you don't necessarily have to write. I usually like to write it. If I ever look back at this problem again, I don't want to question myself of where it went or if I made a mistake and forgot to do part of the problem. But what this tells me is that there is no acceleration in the z direction. All of my acceleration is in the x and y directions. So that path I was telling you about above, which represents our particle moving through space, the shape of that path is dependent upon what types of functions we are using for our components. A few sections ago we learned about lines in space, and the component functions for our lines in space were always linear functions. If you remember, for a line in space, we take the component from our direction vector times t plus the x coordinate from a position vector. And we do this for each of our components. And if you look at what types of functions I'm using here for my components, these are all linear functions because we have t to the first power. So if all your component functions are linear, it's just going to form a straight line. Another one that we see quite a bit is circles. And in order to create circles with a vector valued function, we have to use sine and cosine. So as an example, and I'm going to show you how exactly I figured this out, we're going to sketch a graph of the curve generated by r of t equals 4 cosine ti plus 4 sine tj. If you don't know that, that's a circle. What we can do, let me change this, is we can plug in some different values for t. Remember, this position function, even though it's a vector, it could also just represent a point as well. The components can represent a point. So if you plug in some different values of t, we can see exactly what point we're at on our curve. Because the t is inside of a trig function, we need to use values for t that are going to make this easy to calculate. So I'm just going to plug in 0, pi over 2, pi, 3 pi over 2, and 2 pi. These are just typical values we see on a unit circle for sine and cosine. So if you plug in t equals 0, cosine of 0 is 1, and then we multiply by our coefficient of 4, it gives us an x value of 4, and then sine of 0 is 0. When you plug in pi over 2 for the t's, you get 0, 4. If you plug in pi, you're going to get negative 4, 0. If you plug in 3 pi over 2, you're going to get 0, negative 4. And if you plug in 2 pi, we're going to get 4, 0, which is exactly where we were at time 0. So we'll take a look at this graph. We start at 4, 0, and then we move to 0, 4, and then we're at negative 4, 0. You see we are going around, and then 3 pi over 2, we're at 0, negative 4. So I'm not plotting any t values here, I'm just plotting the x and y values. And then at 2 pi, we're back to 4, 0. So what we're doing here in this vector valued function is it's taking us around a circle of radius 4. We can also change this vector valued function into a rectangular equation, and by that I mean an equation that just has x's and y's. So our first step would be to write this as a set of parametric equations, which is really simple. All we're doing is pulling the component functions out and writing them as their individual functions. So our x of t, the component that dictates our x coordinate, is the 4 cosine t, and our y coordinate is dictated by the second component, so y of t is 4 sine t. But we really don't need the t's here for what I'm going to do next. What I want to do is I want to eliminate the parameter. And anytime you are trying to eliminate the parameter, when you've got trig functions, you should always try to match this up with a trig identity. So since this set of parametric equations have sine and cosine, I'm going to use a trig identity that contains sine and cosine. So I'm going to use the Pythagorean identity that says sine squared t plus cosine squared t is equal to 1. This is always true. That's why it's called an identity. So if I can solve these equations for sine and cosine, then I can replace sine and cosine in this identity equation. So to solve for cosine t, I'm going to have to divide the 4 over. So this tells me that cosine t is equal to x over 4. And same exact thing here, to solve for sine of t, I'll have to divide by 4. So I see sine of t is y over 4. And since sine squared plus cosine squared always has to equal 1, I can replace sine and cosine with the x over 4 and the y over 4. So y over 4 squared plus x over 4 squared equals 1. And we'll just clean this up a little bit. This is y squared over 16 plus x squared over 16 equals 1. And if we multiply through by 16, and I usually like my x first, we get x squared plus y squared equals 16, which is exactly the equation for a circle centered at the origin with a radius of 4.